So you have to convert this into radians per second. So angular momentum is equal to I omega. So you'll figure out what this is. Omega gives you I, so you can figure out the angular momentum. Okay, so torque, just like force, is equal to the derivative of momentum, or change in momentum over change in time. Torque is equal to the change in angular momentum over change in time. So you found the angular momentum here. The angular momentum at the end 0, that gives you a time of 5, so you should be able to figure out the torque. Remember that torque is equal to I alpha. Wait, is there another way to do this? Oh, I think actually there's another way to do this here. I think you want to use D equals V bar T. So you just found the initial speed, final speed 0, gives you a time of 5 seconds, so you could figure out the angular displacement. The work. Okay, work would be just like work is force times distance. Work is going to be the net torque that we found up here times the angular displacement. Or another way you can do it is work would be equal to the change in kinetic energy, so 1/2 I omega squared. So you should be able to figure it that way. It should be the same answer. What external force do you suppose? Oh, this is a conceptual question. I'll let you come up with what you think that is. All right. All right, so it gives you revolutions per second. You need to change it into radians per second. And what happens here is we're dropping this rod onto this spinning disc, and so then it's going to slow down, and after 1/8 of a turn, then they're going to turn together. So this would be conservation of angular momentum. So Li equals Lf. We know what the I of the disk is, which they give us, times omega I, which is what we found up there, and that's going to be equal to I plus the rotational inertia of the rod, which they give us that as well, times omega final. And so you can solve this for the final angular speed. So again, torque is equal to a change in momentum over change in time, and let's see, we know the initial angular speed. You're going to find the final angular speed here. It tells us it goes through 1/8 of a turn somewhere here. I can't remember where that's at. 1/8 of a revolution. So that means that theta would be equal to 2 pi over 8. And so we can use D equals V bar T to figure out the time. Once you know the time, then you can figure out the torque. I wonder if there's another way you could do that. Should be able to do torque equals I alpha too. This would be the I. No, I don't really think we know what alpha is, though, do we? No, I don't think we know what alpha is. Well, I suppose we could do angular kinematics. We could do Vf squared equals Vi squared plus 2AD. We know the final, we know the initial, we know the displacement right here, and so we could find for alpha, and these two should give us the same answer. Nice. Okay, what is the coefficient of friction between? I don't really think I don't know. Can we do that one or not? I think this is a bad question. I don't think we can do that one. I mean, there is a frictional force that's causing the torque. So in other words, this is what I was thinking, that torque is equal to force times the distance. The problem is that distance varies, so it's all the way from the end of the rod all the way to the center of the rod. So I don't know that it would be right to, that would be a kinetic friction force. That would be a kinetic friction force, but I'm not really sure what this is here, this R. I don't think it makes sense to necessarily use halfway out. So I don't think we can do that one. This, you should be able to figure out what kind of collision that is. I'm going to come back to this one real quick because I was watching through the video and I don't think I made it real clear. So yeah, you can do the I alpha to figure out the torque. You can also do the change in angular momentum, change time. But when we're talking about change in angular momentum, I'm not talking about the system because the change in angular momentum of the system is 0. I'm talking about either change in angular momentum of the disc or of the rod. So if you're doing for the rod, the initial angular momentum of the rod is 0. The final angular momentum would be I the rod times omega f. If you're doing the change in angular momentum of the disc, this is the initial angular momentum of the disc. The final angular momentum would be I the disc times omega f. And so then you can figure out the change of angular momentum divided by time. So I just want to make sure you understood that. Okay, number 3 then. So what this is somebody's kind of standing on this merry-go-round at first and they start walking one direction and it spins in the opposite direction. All right, so this is angular momentum being conserved then. The initial angular momentum has to be equal to the final. Well, the initial is 0. In the final, there's two things. There's the final momentum, angular momentum of the person, final angular momentum of the merry-go-round. So for the person, that would be mr squared times v over r. And for the merry-go-round, it's I times omega. And we're trying to figure out omega for the merry-go-round. It gives us what mr squared is. For the person, it says it's 585. So really that's I, the person. It gives us the speed and gives us the radius, which would be 3. We know omega, but it has to be in radians per second. And so you can solve for I. Okay, then the next one here, number 4. The linear momentum of the bullet when it passes through, because it says it, the bullet approaches and leaves, so it kind of shoots through this board here, it decreases. And that's because there's an external force provided by that, that fixed pin right there. The angular momentum is constant. So that's not going to change, and the reason is there's no external torque on the system if we include the system as being the bullet in the blank, which it doesn't say, so therefore it is conserved. It's constant. With what angular speed is the stick spinning after the event? Okay, so initial angular momentum has to be equal to final. Initial would be for the bullet, it's going to be mr squared times V over R. So the R will cancel the square, so it's MRV. It tells us what the mass of the bullet is. Change it to kilograms. We know what V is. It tells us the initial speed. The R would be this distance here. And it says that the bullet shoots through midway through the plank right here. So if the whole thing's 1.2 meters, from here to here would be 0.6 meters. So that means this is 0.3 meters. So R is 0.3. Afterwards, so this is the initial velocity of the bullet. Afterwards, it's going to be MRV, but this is the final velocity. Again, this is 0.3, and this is for the bullet. So make sure that's in kilograms. Plus, I of the what do we call this? The plank, which they tell us what that is, times the final angular speed. So we could solve for the final angular speed. All right, to figure out how much energy is dissipated, we want to figure out the change in kinetic energy. And so that's going to be 1/2 the mass of the bullet times the final velocity squared plus 1/2 I omega final squared. So that's the final kinetic energy. And then minus the initial kinetic energy, 1/2 mass of the bullet times VI squared. Now this is going to give us a negative, so absolute value of this would be how much energy is dissipated. Okay.